So let me just start by reviewing digital signatures. Which is a method to verify a document is authentic. So what is not encrypted is the document, but what needs to be verified is that the individual or organization that sent the document or claims to have sent the document really did so.
Professor,
Yes?
I think someone has a question. He just wrote it on the chat.
Okay, hang on one sec. The chat says I have no questions.
Oh, my bad. I misread it.
So the digital signature schemes that come from the RSA public key crypto system and another that's based on the El Gamal public key crypto system. And the one we looked at is based on RSA. And the idea is the following. So Samantha sends Victor a document. So D gets the document. But Victor needs to be sure that it's really Samantha that sent him the document and not someone else who might have evil intent. So Samantha wants to sign the document. And Victor wants to look at the signature on the document and know that it really came from Samantha and no one else. So the method is based, just as the RSA public key crypto system is based, on the fact that factoring an integer is hard, multiplying integers is easy. So, and some elementary number theory that all of these crypto schemes that we've talked about are based on. So here is a document. Anyone, Victor, everyone in the world can see this document, but the problem is to prove that it was really Samantha who sent the document and no one else. So Samantha chooses secret primes P and Q. So this means primes that she knows, but she's not going to tell anyone else. And she multiplied them. So you get a number n, which is P times Q. Anyone who knows P and Q can multiply them and get n. There's nothing special about that. But Samantha is not going to tell anyone what P and Q are. Samantha is going to publish this number n. So everyone knows what n is, and everyone knows that n is a product of two primes, but they have no way in any reasonable amount of time to factor n to find out the primes. So again, the key idea is multiplying P and Q to get the number n is easy and fast. Factoring n to get P and Q is hard and takes forever. And I put a question mark is takes forever as far as we know, because there is no proof that factoring is hard. Cryptography is based on problems that are hard to solve as far as we know. What that means is lots of smart people and lots of organizations that are well-funded and well-equipped and fully staffed have tried to solve the problems and not been able to. As far as we know, there is no proof that factoring is hard, but no one has ever published a fast factoring algorithm that works on a conventional computer. There is a factoring algorithm that would work on a quantum computer if a large quantum computer could ever be built. And there are small quantum computers, but they're not yet anywhere close to having the power to factor a number, even though it would be very easy to do. So as far as we know, but this is purely human experience, it's not mathematical proof, factoring n to find the primes p and q that made up n is hard and would take forever on a conventional computer, right? So that's the key idea for the RSA crypto system and for the RSA digital signature. Okay? So Samantha takes two primes p and q, multiplies them together, and gets n. Okay, because Samantha knows p and q, she can also, if she knows p, she knows p minus 1. If she knows q, she knows q minus 1. So she can multiply those two numbers together. Right? And if p and q are big, so we choose these secret primes p and q, and these are large primes. They have hundreds or thousands of digits. All right? P minus 1, q minus 1, you multiply them together, you get a big number. And then Samantha chooses a number e such that the GCD of e as the greatest common divisor and p minus 1, q minus 1 is equal to 1. So e is this number that Samantha calculates, and she publishes it. So what is in the public domain? What does Victor know? Victor and everyone else knows the document D. He only needs to verify its authenticity. Samantha needs to sign the document in such a way that everyone will know it's her signature and no one can forge her signature, right? So you don't want someone who can forge Samantha's signature, send a bogus document with Samantha's forged signature, and everyone will be misled into thinking that the bogus document is really the real one. So Samantha sends this document, and then to get her signature, she's going to do three things. First, she chooses primes p and q, multiplies them together to get this number n, which she publishes. She multiplies together p minus 1 and q minus 1. There will be a huge number of integers e that are relatively prime to p minus 1, q minus 1. So Samantha chooses an integer e whose GCD with p minus 1, q minus 1 is 1, and she publishes the number e. Okay. And then what does Samantha, so everyone knows these three numbers. Then what does Samantha do? Samantha solves the congruence EX congruent to 1 mod p minus 1, q minus 1. She looks at this number and she wants to solve this linear congruence. And why does she know and why do we know there's a solution? Because the number e is relatively prime to the modulus p minus 1, q minus 1. Okay? So this solution, this congruence has a solution, and let D be a solution. So that D satisfy the congruence d times e, or e times d, dE congruent to 1 modulo p minus 1 q minus 1. Now, why can someone else not get this number d? To get the number d, you have to know p minus 1 q minus 1. You get that only by knowing, in effect, what are p and q. You can only get the primes p and q by factoring n, and no one knows how to do that. So Samantha knows this number d such that d times e is congruent to 1 modulo this. And this number d, that's Samantha's secret. So Samantha's secret is the number p, the number q, and this number d. All right. And what is the signature? So Samantha signs the document D by computing the document. Remember, every document is a digit, it's an integer. Right? Everything has been converted into binary. Every document's a sequence of zeros and ones, which is a binary digit. D, capital D, to the power D modulo n, and call that S. So D is the document. Everyone knows that. N is a modulus. Everyone knows that. Little d is a secret number that only Samantha knows. She takes capital D, raises it to the power D mod n, takes that number S, reduces it mod n. That's the signature. And she sends S out into the world. She publishes S. So what the world knows, and Victor in particular, so everyone knows the document D, the integers, or the numbers, N, E, and the signature, S. So the problem is, how do you verify that S is, in fact, Samantha's signature? And what you do is you compute S to the power E so Victor, or the public at large, compute S to the power E mod n, because everyone knows the document, everyone knows N, everyone knows E, and everyone has gotten the signature S. And what is this supposed to be? Well, recall that S is congruent to D to the D mod n. So S to the E is congruent to D to the D to the E, which is D to the D times E mod n. But DE is congruent to 1 mod P minus 1 Q minus 1. And recall, N is equal to P times Q. So phi of N is phi of P times Q. This is the Euler phi function. And phi of PQ is P minus 1 Q minus 1. So by Euler's theorem, if the GCD of D and N is 1, then D to the phi of N is congruent to 1 mod N. That is, D to the P minus 1 Q minus 1 is congruent to 1 mod N. But DE remember, DE is congruent to 1 mod P minus 1 Q minus 1. So DE is 1 plus some multiple of P minus 1 Q minus 1. That's what a congruence means. So D to the P minus 1 Q minus 1 is D to the 1 plus P minus 1 Q minus 1 K. That's D times D to the P minus 1 Q minus 1 to the K. This is congruent to D times 1, or congruent to D mod N. So S to the E is congruent to D mod N. So again, let's understand, let me just summarize what's going on. Samantha sends some document D to Victor. She also sends the numbers N and E to Victor. She computes D, which she doesn't tell anyone. And she sends to Victor her signature S, which is D raised to her secret power little d mod N. And this is her signature. She got it because she knows little d. If you don't, how do you get little d? You solve a congruence modulo P minus 1, Q minus 1. You get that congruence only if you know P and Q, only if you can factor N. No one can do that. So no one can compute little d, so no one can compute capital S, the signature. And how do you verify this? You compute S to the power E and you get back, if you get back D, then you know the document D really did come from Samantha. So that's what's involved. Now, any questions about this? This is the RSA digital signature. And I want to point out one practical difficulty with this, which is, so we have a kind of a practical difficulty. D could be a huge file, and computing, raising that to a power D mod N might be too hard to do. That might be too hard to implement on your computer. So there's something that people talk about in computer science called a hash function.
Professor,
Yes.
Can you explain me that once Victor got D, what he does?
So Victor gets the document D,
Mm-hmm.
has these numbers N and E, which are in the public domain,
Mm-hmm.
and he gets the signature from Samantha.
That's
So,
bogus signature.
so he gets the number S from Samantha.
That's bogus signature, not the real.
It's the real, I don't know what you mean by bogus. This is the signature that Samantha sends to Victor. He
Okay.
needs to know, he needs to prove. So this is how Samantha calculates the signature, but all Victor gets is the number S.
Okay.
And how does he verify that S came from Samantha? He knows E, he knows N, he knows D. He computes S to the power E mod N, and he sees whether or not it's equal to D. If it is equal to D, he knows the signature is authentic. If S to the E is not D mod N, then it is not Samantha's signature.
Okay.
Okay. But here is a practical difficulty. It's this document you want to verify. A document can be huge, can be enormous. And to compute the signature, you have to take that document and raise it to the power D. And that might be just a ridiculously long, costly calculation. And you want to find a more efficient way.
So lowercase d is chosen by Samantha?
What?
The lowercase d is chosen by Samantha?
It's not chosen exactly. The lowercase d is a solution to the congruence. D, so it's that d times e is congruent to 1 mod p minus 1 q minus 1. So Samantha knows this. She knows the modulus. She knows E. She has to solve this congruence.
Oh, okay.
And the solution of this congruence is the number D. And only Samantha knows that. Nobody else does.
Okay.
Okay.
Thank you.
Okay. Now, the problem, sort of the practical problem, is that D could be a huge file. And raising D to the power little d and reducing mod n might take too long. Might take too much time and possibly even space. Time and space are the two parameters you're concerned about in computer science. How much time something takes, how much memory you need to use. So computer scientists have something called hash functions. And I'm not going to give an example of how to construct a hash function, but just so for general sort of background and knowledge, a hash function is something like this. You might have a big file D, and you have some function that produces, so this is big, and this produces some function, I'll call it h of D, which is a small file. And this hash file, this hash function, has some good properties and some bad properties. First of all, if this is big and this is small, then there exist other files D prime where h of D prime is the same as h of D. So this hash function is never one-to-one. So you could have a completely different file which has the same hash function associated with it. So these files are different, but these hash functions collide. So you want a hash function with few collisions. That is, among the documents you're likely to look at, you want them generally to correspond to one and only one hash function, one hash file. So in practice, instead of computing d to the power d mod n, you take the hash function h and calculate h to the power d mod n. And this is the signature that Samantha sends. So in addition to transmitting or making public the document D, you also make public the hash function of that document, H, which is a smaller file. So computing D to the D and computing S to the E then become reasonable calculations. That's the game. Okay. So again, this is just something for your to be aware of. In computer science, one deals with these things called hash functions associated to a function. They're much smaller functions, and they're not uniquely determined by your original document, but it should be relatively rare for two documents to have the same hash function. So you can replace a big document by a small document for purposes of verification. You cannot recover D from the hash function, but you can determine the authenticity of something by using its hash function. So that's the moral of that little story. And let's see. I think I had assigned, let me just find the homework. There we go. So I had assigned a couple of problems, 4.1 and 4.2, on this subject. And let me actually do the homework problems, at least the first one. So
Yeah, please.
So this is exercise 4.2 on RSA digital signatures. So Samantha chooses primes P equal 541 and Q equals 1223. Her public modulus is N equal P times Q. So I could use a calculator, but I'm just going to use Maple because I like Maple a lot. So I think you can see the screen. Let's see. So P, oops. P is the prime 541 and Q is the prime 1223. And N is P times Q, which is 661,643. And E is the number 159,853. And it's supposed to be the case that E is relatively prime to P minus 1, Q minus 1. So let's just verify that. What is the integer greatest common divisor, IGCD, of E and the product of P minus 1 times Q minus 1? It's 1. So that looks fine. And what is her private signing key? So N is the public modulus. What is D? D has to be a solution of the congruence D times E. Let me do it like this. So if you look at the remainder, the integer remainder of D times E with the modulus P minus 1 times Q minus 1, that has to be equal to 1. DE has to be congruent to 1 mod P minus 1 Q minus 1. All right. So that doesn't make any sense. So let me just, because you must have had something in the memory. Let me just clear everything. So this is P and Q, this is N, this is E, this is the GCD. And I'm saying find a number D such that the greatest, if you take D times E, that's 159,853. The integer remainder of that with 659,880, that's my P minus 1, Q minus 1, is E. So somehow I have to solve this congruence. So I can solve it by hand using the Euclidean algorithm. I don't know if I can solve it in Maple. Let's just see. I'm curious whether Maple has a command that would let me solve that congruence. So let me go to help.
Professor, you want to solve for D, right?
Yes.
So you raise e to the power minus 1 congruent p minus 1, q minus 1.
Yeah, but what is that?
That's D.
Yes, but how do you compute that?
Yeah, so type it. When you type e to the power minus 1, you type mod p minus 1 times q minus 1.
Okay, so let me just let me just see what comes up when I use help. So let me look at congruence.
Okay.
So let me look at linear congruence. I don't want the definition. Let's see what this is. Let me see what you said. There's a mod command.
So I usually type it.
Sorry?
I usually type it. I don't find a command. So I usually type it. If you type MOD, it's space, it's modulus.
Let's see. So you're saying if I do something like 17,
No, E is not 17, Professor.
I don't know, I just want to test this.
Yes, yes,
17 mod 5.
yes.
Oh, it gives
Semicolon.
2. Oh,
Yes.
that's interesting. Okay. So, and so let me just, so I don't have to keep writing P minus 1, Q minus 1. Suppose I let M be equal to P minus 1 times Q minus 1. Okay, so that's my M. So you're saying if I write e to the power minus 1 mod M.
No, you put D. It's not mod. You put D. Yes.
E to the power minus 1 mod M.
So you got it.
So it doesn't like E. So let me put this number. So this says that the inverse is 561, 417. So that's the number. That's the private signing key D.
Right.
Okay. So thank you. I didn't know that mod command was so simple, even that it existed. Very good. So that gives me the private signing key. That's little d. And S, the digital document is, I can't use D in Maple because that stands for derivative. But if I take 630579 and I raise that to the power 561,517, and I want that mod N that should be the signature S. So that's the signature. Is that what you got?
Yes.
Good. Okay. So I'm using a computer to solve these congruences. On an exam, if I give you a problem like this, which is likely, the numbers will be much, much smaller, so you can do it by hand. But it's nice to know that any computer program that you're familiar with, and certainly Maple, will be able to do all these calculations for you.
So that's my question. Will you accept us to use, Maple to do the calculation without
I said on
justifying?
the review sheet that on the exam, it's an open book exam, and you can use calculators and computers.
Okay. So if we put answer directly, that would be okay, or we have to justify?
You have to answer the question. So if I ask you to justify it, you have to justify it. If I don't ask you to justify it, you can just write down the correct answer.
Okay, thank
It
you.
depends on how the question is phrased.
Thank you very much, Professor.
Any questions about this? So let's see. So this was, let me just put it on this. Cryptography exercise 4.1. So let me, oops. Let me do cryptography exercise 4.2. So in exercise 4.2, we have a public modulus n, which is equal to 1,562,501. And the public verification exponent is E equals 87,953. And we have documents D prime, D double prime, and associated signatures. So in the first case, we have a document let me call it doc like that because I can't use D. Document 1, which is 119,812. And signature 1 is 876,453. And the question is this a valid signature? So how do we compute that? We compute S1 raised to the power E mod n. Let's try it like that. S1 to the E mod n. And in fact, we didn't get the document. So this signature is not valid. Okay, let's look at the next case. Document 2 is 161,153. And signature 2 is 870,099. So I want to compute signature 2 raised to the power E, which is mod n. And that is dot 2. So when I take S1, S2 to the E mod N, I get back the document. So signature 2 is valid. The third document is 586-036. And the third signature, S3, is 602-754. And if I compute that signature, S3, raised to the power E, oops, I need a capital S, S3 to the power E mod N, I also get back the correct document. So signature 1 is valid, but signatures 2 and 3 are not. Any questions about that? Now I have a problem here because my mouse doesn't seem to be working. Oh, now it's working. Okay. So stop the share. And good. So that was problems 1 and 2 in the homework. Okay. Okay. By the way, someone in the lecture last time told me if I'm on a website and I click on something, I can see something about a digital signature.
Yes, I said that last time. If you see in the address bar, if the clock sign, HTTP, before HTTP, a clock sign, sorry, a lock sign. If you click
Okay.
the lock.
Oh, I see. So I just clicked on something. It said encryption with
Or
a digital
connection is
signature
secure.
keeps information private. Show certificate.
Connection is secure.
I have something that says there's a signature. It says this certificate is valid.
Yes,
Okay.
the valid certificate. Yes.
So it's that lock sign. And,
Yeah.
oh, that's interesting.
Mm-hmm.
Let me see what the New York Times says. I'm going to the New York Times website.
Sure.
So it just says show certificate. So it just shows your certificate. Oh, it said issued by Wade RSA, California. So
Right.
it says the New York Times seems to actually be using this RSA digital
Right.
signature.
Mm-hmm.
Oh, that's fascinating.
Mm-hmm.
Huh.
You can see Google.
So looking at the Wall Street Journal, Wall Street Journal is using Amazon RSA.
Right.
Huh. Let me see what I just went to the Lehman Library.
Mm-hmm.
They're using somebody else's RSA. Wow.
Mm-hmm.
So it seems that it really is true that But it was,
Yeah.
I just looked at something else. Oh, I looked at something else, which is not using, it's using a different digital system, digital signature.
Mm-hmm.
But the RSA is certainly popular. Oh, that's really good. Thank
Right.
you.
Yeah.
Hmm.
Welcome. Most of them are RSA.
Yes, yeah.
Mm-hmm.
At least from the small sample I just did, not a large sample, but that was interesting. Okay. I wanted to do a couple of knapsack problems also. So let me try to find the homework again. Okay, so 7.2 and 7.3. Okay, so
Can you go through, like, if I know R1 and R4, how to get all the R's?
that was from the review sheet.
Mm-hmm.
Okay. So there's not a unique solution to that, but there are many there are many solutions. So
Yeah, it can be anything. You just double it and make it a little bit bigger.
a little bit bigger than twice as big.
Yeah, twice. You make it twice, and then something you can add. So there is no particular
Right.
answer, right?
So if you have you want four numbers. R1, R2, R3, and R4. So you're told and R5. So you're told you have a super increasing sequence, or you want to construct a super increasing sequence where the smallest number is 11 and the largest number is 200. So the simplest thing to do, since you have an upper bound, is pick each number as small as possible. So the second number has to be at least 2 times the first number.
Like
So
23, suppose.
if you want a little bit bigger, 23. The next
Okay.
one has to be bigger than 46, so you can make it 47.
Mm-hmm.
The next one should be bigger than 47 times 2. That's
Mm-hmm.
94, so make this 95. And
Mm-hmm.
200 is bigger than twice 95.
Right.
That would do it.
Correct.
You have to be a little bit careful. Let's see. If you made this 24, this would be 49. This would be 99. It still is okay. If you
Yeah.
made this 25, this would be 51. This would be 102, and this wouldn't work. So
Thank you.
23 or 24 would be fine and give you a system, but you have to be a little bit careful to squeeze it in, that the numbers don't grow so big that your number for R5, the fifth number, is not valid.
Mm-hmm. And number 9, you said, like, R is given, M up to 8, I to 8, not,
Oh,
but the
by the way, I
actual.
should have back on this. You could also, R2 doesn't have to be bigger than twice that. You could have made this 22. And then this could be 44. And this could
Equal
be
also.
88. This would still be okay.
Yeah, equal and bigger.
Yes. So in
Okay.
problem number 9, each number is exactly twice the previous one. So these are the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256. And you choose A equal to 11 and B equals 600. So, and you want to define a sequence M. See, how many numbers are there? This is R1, 2, 3, 4, 5, 6, 7, 8, 9.
9.
So you're going to have numbers M1 up to M9, and M sub I is going to be congruent to 11 R sub I mod 600. Right? So
You said up to M1 to M8. Is this M8 or M9? It should be M9.
M9.
Oh, okay, thank you.
Yeah. Right. So to construct this, can't quite do it by hand, but let's see, M is going to be, first number will be 11, 22, 44, 88, 16 times 11 is 176. And then you're going to have to reduce, 36 times 11 is 396. 64 times 11 is 704. If you reduce that mod 600, you get 104. 128 mod 11 is 1408. If you reduce that mod 600, you get 208. And 256 times 11 is 2,816. If you subtract 2,400, you get 416.
That's right.
So this is 1, 2, 3, 4, 5, 6. So this is the sequence M. And it's ordered. You can't rearrange the numbers. If you rearrange the numbers, everything is wrong. So this is part A, which I guess wasn't so hard to do by hand. That's nice. Part B is to take the plain text X equal to 1101, 01001. And then you take what is the dot product X times M. So this means you multiply these vectors pairwise, coordinate-wise, you get 1 times 11 plus 1 times 22 plus 1 times 88. I don't even need the ones. 11 plus 22 plus 88. Skip 1 plus 396.
That's it.
Skip 2, and then the last one plus 416. Right?
Mm-hmm.
So if you add this up, let's see. This is, I'm just doing it on a piece of scrap paper. 396 and 416 is 812 plus 88 is 900. So you get 933, I think. Right? So that is the encrypted binary sequence. And to decrypt it, we have to compute S prime congruent to A inverse times S mod B, and the B was 600. So let me do it the lazy way, taking advantage of the fact that I just learned the mod command. So let me share the screen with my Maple here. I have A, which is 11. So I have 11 to the power minus 1 times my S, which is 933 mod 600. And that gives me 303. So S prime is 303. So I go back to my original sequence R, and I need to write 303 as a sum of element, as a subset sum from this sequence. So 303 is equal to
1 plus 2.
well, you always start with the biggest number and work backwards. 256
Okay.
plus, let's see, if I add 64, it's too big. So plus 36, that is 292 plus 16 plus plus 8 plus 2 plus 1. Is that right? Let's see. This is 256, 292, 302, 303. So if I write this now in the proper order, this is 1 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8. What's this 36? Oh, I don't know. 36. Sorry, 32. This is, yeah, I messed this up, right? I wrote down 36. So 32 times 11 is 352. So this should have been 352. And that was element 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this should have been 50. Someone should have corrected me. This was wrong. So I hope this is now correct. Okay. So 1, 2, 4, 8, 16, 32, 64, 128, and so forth. So when you multiply these numbers by 11 and reduce mod 600, 32 is 352. So this was x times m, 1 times 11, 1 times 22, 1 times 88, 1 times 352, and 1 times 416. So this is not 303. That's wrong. This is 768.
889.
Plus 88 plus 22 is 110. Plus 11 is 121.
889.
So I get 889. Thank you. 889. So I want to calculate. Let me go back to my maple. Let's need to do this correctly. This is 11 inverse times not 983, but 889. And that is 299.
Yep, now it's good.
Okay. So I want to write 299 in binary. So that's 256. Let me do it here so it's on the same sheet. So 299 is 256 plus
32.
43. So plus 32 plus 11 plus 8 plus 2 plus 1. So this is 1 times 1, 1 times 2, 0 times 4, 1 times 8, 0 times 16, 1 times 32, 0 times 64, 0 times 128, and 1 times 256. So 299 corresponds to the sequence 1, 1, 0, 1, 0, 1, 0, 0, 1. So S prime was 299. And in terms of the original super increasing sequence R, that corresponds to this binary string. 1, 2, 3, 4, 5, 6.
Can you
One.
scroll up?
Is that correct?
Yes, but yeah, we cannot see it. Yes, that's great. Thank you.
Okay. Okay.
I just check with the R, you know, if they take the R and the given sequence X, I just multiply it to check 299.
Right, good.
Yeah.
It's great when I have a crew of people helping me with this. I like that.
Yeah, it's easier.
Well, it's not so much that it's easier. It's like you can find out, someone can tell you you made a mistake, and then you know to go back and check everything and make sure you get the right answer.
Right.
I mean, checking is important. And
sure. Thank you.
Okay. Is there anything else we should do today? I have an office hour tonight and one tomorrow night at 7. On Wednesday, I actually have some medical appointments in the afternoon. So I can only meet for cryptography at 10 o'clock for a problem session. And I might also make one on Wednesday evening, but it wouldn't be, depends when I get back from the doctors, but it might not be till 8 o'clock or later, but I'll put something up online. But certainly tonight at 7, tomorrow 11, tomorrow night at 7, Wednesday morning at 10.
That's fine.
Good. Okay. That's all
Thank
for today
you.
then.
Yep.
All right,
Thank you.
see you all later, I hope. Bye-bye.
See you. Bye.
Bye-bye.